Welcome to this lecture. This is the fourth lecture of week 8. So far, we have been concentrating on the special case of weak convergence of random variables that we have seen in the form of the central limit theorem. And as part of those discussions, we have also seen some nice applications of the results involving the weak convergence of random variables. We have also seen the extensions of similar results in the higher dimensional setting. Now, here you note that the properties of weak convergence, specifically about our understanding about equivalent formulations of weak convergence, played a very important role. In particular, in the results involving the central limit theorem, we have actually considered the pointwise convergence of the characteristic functions. So, that is through the Levy's continuity theorem, we are talking about the corresponding weak convergence. Note that we have also talked about certain further properties of weak convergence in terms of scalar multiplications and other important properties. Now, here in this lecture, we are going to look at certain further advanced results involving weak convergence that are motivated by our discussion on the central limit theorem. However, these results are quite advanced, but it is for your information that we are going to discuss these results without proof. So, let us see these results one by one. All right. So, our idea now is that we are considering the weak convergence of random variables and random vectors, and this mode of convergence we have concentrated our attention on equivalent formulations either through the pointwise convergence of the distribution functions to the limit distribution function, but only at the points of continuity of the limit distribution function, or through the pointwise convergence of the corresponding characteristic function. In this setting, we now recall a specific type of an approximation of distribution functions, which we have discussed earlier in remark 6 of week 5. So, there what we had used was something called empirical distribution functions. So, let us recall that setting of that result. What we are saying is that suppose I start with a sequence of IID random variables, call it yn. So, now since they are having identical distribution, they will have a common distribution function, which we denote by capital F. Now, fix a point x in the real line and look at these type of random variables. What we are doing is that we are first focusing on the event that the nth random variable yn is less or equal to x, and we are just looking at the indicator of that. So, since this function depends on yn, this is a random variable. Moreover, this is only a 0 or 1 valued random variable. So, we have discussed this earlier in remark 6 of week 5 that the distribution of these new random variables, the indicator random variables, is actually Bernoulli with probability of success given by exactly the distribution function capital F evaluated at the point small x. So, here all these random variables capital X n superscript small x are independent and identically distributed with exactly this distribution. Now, what we had seen earlier as an application of the strong law of large numbers that we had discussed earlier, we established the convergence of these kind of quantities, where we are simply looking at the sample mean of this sequence of random variables. And here, since this sequence of random variables capital Xn's superscript small x, these are IID, we are appealing to the strong law of large numbers and claiming that it converges to the corresponding mean. And here the mean of these random variables is exactly f of x. Now, this convergence happens in the sense of almost sure convergence. So, the empirical distribution functions converge to the function f. So, here the convergence is done for every fixed small x, and the convergence is through the notion of almost sure convergence. Note that the limit value is degenerate, whereas the f n of x is a random variable. alright. So, we also can consider this type of convergences in the L2 setting or in the convergence in probability setting. Now, if we appeal to the Lindeberg-Levy central limit theorem, which we have discussed earlier in week 7, then we can actually have a certain kind of rate of convergence for the above convergence that we have mentioned. So, again we are going with a fixed x in the real line. Look at the difference. So, the difference is actually that this is essentially a kind of a sample mean and f x that is playing the role of expectation here. So, if you scale everything by square root n, the classical central limit theorem or the Lindeberg-Levy central limit theorem is going to tell us that it is going to converge in distribution to z, which is following the Gaussian distribution with mean 0 and with this specific variance as n goes to infinity. So, here how did this variance term arise? So, remember the type of distributions we are considering is Bernoulli with probability of success given by f of x. So, here the expectation is exactly f of x, that quantity, and the variance is exactly f of x times 1 minus f of x. So, therefore, that is how we are going to end up with this limiting distribution. So, this limit is following through the classical central limit theorem as n goes to infinity. But now, this is essentially telling us that the relevant rate of convergence that we have pointed out earlier for the convergence of the empirical distribution functions to the distribution function capital F, that actually we can be considered in the rate square root n. Now, this form of convergence, as we have also pointed out, is in the sense of weak convergence. Now, what we are going to consider is a stronger result that is going to look at these type of convergences, but uniformly in x. Note that the earlier discussion that we just completed, that tells us that we are fixing small x in the real line and then we are looking at the corresponding convergence. Now, the stronger form of this result that we are going to look at, there we are going to look at these kind of error bounds or the type of convergences uniformly in the x variable. So, we are going to skip the proof of this result, but discuss it. So, let us see this result. It is typically called Glivenko-Cantelli theorem. All right. So, we continue with the same setting, that we have some appropriate IID random variables through which we have now considered the corresponding empirical distribution functions, and we are interested in the convergence to the actual distribution function. Now, note that we are now looking at this kind of errors, but with a additional supremum outside. So, this is going to give us the uniform distance in some sense from the empirical distribution function from the actual distribution function. So, this is the uniform type of convergence that we are talking about, and this result, the Glivenko-Cantelli theorem, is telling us that this convergence happens that as n goes to infinity, these random variables converge almost surely to 0. So, this is quite a nice result that is giving us that there is a nice convergence uniformly in small x of the relevant empirical distribution functions to the limit distribution function f x. All right. Now, in the setting of this result that we have just discussed, we can now ask explicitly about the rate of convergence of the central limit theorem. Remember, we had motivated the central limit theorem to be the rate of convergence type result for the law of large number setting. Now, we are saying that we have obtained that rate of convergence, but now central limit theorem itself is a convergence type result, and now we are asking what is the rate of convergence for the central limit theorem. And the next result that we are going to talk about actually talks about such a rate in a explicit form like this. So, let us see. So, here we are going to make certain additional assumptions that the third absolute moment actually is finite. So, again we only discuss the result and the proof is not included in the syllabus. This theorem is due to Berry as well as Essen, and we typically call it the Berry-Essen theorem. Alright. So, this is the setting that we are going to again consider a sequence of IID random variables, and we assume that all of these are in L3, meaning if you look at expected value of modulus of x n cubed, these quantities are finite, and since we are considering identical distributions, this quantity is independent of n. Alright. So, now let us look at the distribution function of the corresponding centered and scaled version of the sequence of partial sums. So, what we do is that we subtract out the expectation and divide by the square root of the variance. Denote the distribution function by capital Fn. Now, remember this kind of centered and scaled versions, if we wish we can also write it explicitly in terms of the moments of the random variables x n like this, that the expected value of S n now is nothing but n times expected value of x 1, and the variance of S n is again n times the variance of x 1. So, we can write down this expression in terms of the appropriate moments of x 1 itself. So, here S n as always is giving us the sum of first n random variables. Now, the result states that if we want to talk about the convergence to the Gaussian random variable in the sense of weak convergence, we have to look at the error from the distribution function of the Gaussian random variable. So, here as always our z denotes normal 0 1 random variable, and f of z of course denotes the corresponding distribution function. So, what we are now saying is that the distribution function of the centered and scaled version of S n, which is f n of x, away from the distribution function of standard normal random variable z, that error uniformly is dominated by this quantity. So, note here first of all that we have used the fact that the random variable x n's have finite third absolute moments, and here this quantity appears in the numerator. Moreover, the variance also appears in the expression. So, this quantity here is dependent on the distribution of the x n's. Now, there is also a constant that appears in the calculations in the estimate. Now, here this constant is actually a universal constant, meaning it does not depend on the distribution that you have chosen. So, it is not dependent on the distribution of the x n's. So, this is a very interesting constant that comes up. And finally, the estimate gives you this rate of convergence through the square root n factor. So, this explicitly gives you the appropriate rate of convergence for the central limit theorem, specifically the IID setting that we have discussed earlier, that in terms of the square root n factor, but with this additional assumption of finite third absolute moments. Now, we are not going to discuss the proof, but it is interesting that the explicit value of this universal constant c is not yet known. Up to the present knowledge, what we are aware is that the value of this constant is between these ranges. Originally, the results that were proved by Berry as well as Essen separately, they had given certain nice upper and lower bounds, but now that has been improved and improved to this range, but to this date the exact value is not yet found. So, this is a open problem in this setting. Alright. Now, we also can talk about the errors in the setting of central limit theorem in another sense. So, the theory of large deviations tries to interpret some such error. So, this is an important extension of the type of discussion that we had in the central limit theorem setting. So, again we discuss this in a simple setting of IID sequence of random variables. Again the extensions to the random variables, general sequences of random variables are also known, but with additional appropriate assumptions. So, now what we do is that we now ask what is the rate at which this kind of probability decays with x. So, let us clarify. So, what we are saying is that look at the corresponding sample mean. Now, the idea is that this sample mean through the law of large numbers type result that we understand will be essentially close to the expected value of x 1. But now, suppose your small x is greater than this mean value. So, we are now considering large small x. So, that will give us certain probabilities involving this sample mean that we are interested in. We look at it in the log scale and divide by n. Now, here in the theory of large deviations, what we are interested in is the limiting value of this quantity as n goes to infinity, and we are actually interested in the values when x is large, and this ideally would give us certain kind of decay in the x variable. So, for large x I should get a very small value. So, this topic again is not included in this course, but this also tries to capture some kind of error bounds in the central limit theorem setting. All right. A final result that we want to talk about actually gives us certain kind of nice growth bounds on this sequence of partial sums. We are not going to talk about the proof, but let us discuss the type of results that it gives. So, this is called the law of iterated logarithm. Again we are going to consider a sequence of IID random variables with mean 0, and let us for simplicity work with variance being 1. Then the result states that if you look at modulus of Sn divided by this quantity, which involves square root of 2n times log n. So, this ratio, if you look at the lim sup of that as n goes to infinity, that will be 1 almost surely. So, this is called the law of iterated logarithm. So, in this course we have looked at many interesting results involving convergences of random variables as well as random vectors. But the type of convergences that we have discussed involves mainly certain specific modes of convergence, namely almost sure convergence, convergence in LP, convergence in probability, and finally, the notion of weak convergence, which is also called the convergence in law or convergence in distribution. We had looked at further properties of these type of convergences and also discussed nice examples. In particular, the special cases of these convergences that we have seen led us to the results involving the law of large numbers and the central limit theorem. Remember, the law of large numbers we had discussed in these two forms, when the convergence is either in the form of almost sure convergence, that is the strong law of large numbers, and when we are considering the convergence in probability setting, that is the weak law of large numbers. And of course, the central limit theorem has been discussed through the notion of weak convergence. Now, along the way we had also looked at other interesting properties involving characteristic functions, independence of events as well as random variables, and their connection to product measures. So, these are all the type of things that we have discussed in this course. Now, as a follow up of this course, you may consider further advanced topics such as stochastic processes in discrete and continuous time. This may include things of this kind, that you may focus on Markov processes, martingales, and stochastic calculus. Also, you can also talk about further applications of probability in other branches of mathematics. Remember, as a consequence of the law of large numbers, we have discussed about normal numbers, which is giving us some nice application of probability to the setting of number theory, right. So, the idea is that probabilistic techniques are quite useful if you are dealing with certain combinatorial problems. So, the type of results that we have discussed in this course, I hope should be useful in your further studies. We stop here. Thank you.